Bismillahirrahmanirrahim. Assalamu alaikum. I'm Fakhr Lodi and this is our 33rd lecture of Formal Methods for Software Engineering. In the previous lectures, we have been discussing algebraic specifications. And we saw different algebraic specification techniques. First, discussing algebraic specification from a generic point of view, and then discussed couple of algebraic specification techniques and tools, including large and OBJ. आज हम एक नई टेक्निक पे बात करेंगे स्पेसिफिकेशंस की एंड फॉर्मल मेथड्स की, which is totally different from algebraic specifications. This technique is called model-based specifications. In the algebraic specifications, we specify the system or the entity in terms of its external behavior, in terms of the inputs and outputs, in terms of the sort of functionality that is provided by this particular entity that we are discussing or that we are specifying. So, वो algebraic जो entity है, उसको हम external behavior के तौर पे हम उसको discuss करते हैं, and we say that if we gave it this input, this is what we would get. Another very important aspect of algebraic specifications is that the algebraic specifications, they do not have any side effect. They are free of any side effects. What does that mean? That means we are not talking about any changes to any of the variables or any of the state of the entity that we are discussing or that we are writing specifications for. So there are no side effects in this particular case. So algebraic specifications, they specify the entity from an algebraic abstraction point of view. So we specify abstract data types with the help of algebraic specifications. No internal state is comes into play there, and we do not talk about the internal state of the object in that particular specification. On the other hand, this new technique that we are going to discuss now, and then we are going to spend a lot of time on this technique, we'll be discussing and looking at many examples of that. That is the model-based specifications. In this particular case, the system is defined in terms of the state space. So the model of the system has what is called the state space. What does that mean? That means all the variables that define the current state of the system, as well as the entire possible values that it can have, that is given to you by the type of that particular data that we have. So we define this thing in terms of the state of the system, and then we say, okay, if we gave this system this output, or if we performed this particular operation onto this system, how would that change the state of the system? How the internal variables that are used to store the state of the system would be affected by that particular operation. So we are not just talking about the behavior of the system from an external point of view, but we are also talking about the system and giving its behavior, specifying its behavior with respect to the internal state that is maintained within that entity. Model-based specifications, they are relatively easier and more intuitive because they map very closely to our programming paradigms. The programming, the kind of programming that we are used to. For example, when you write program in C++ or Java or that kind of language, the imperative programming paradigm, in this particular case, in the object, we have the state of the object. There are certain instance variables which maintain the state of that object, and we talk about that particular state in terms of the operations that we have, and then we say that these operations, they modify the state and we specify how that modification takes place. So this is what we have in what is called model-based specifications. Since they map very closely to our imperative programming paradigm, hence people find them easier to follow as compared to the abstract algebraic specifications. So what we are going to do is we are going to look at one very ancient model-based specification language, which is very mature and has been there for a long time, and it has inspired a number of other model-based specification languages which are now used more extensively. So this model-based specification is known as VDM, Vienna Definition Method. What is Vienna Definition Method? Let us try to look at this slide and try to understand. I'll give you a brief history and then I'll give you an overview of what VDM is. We are not going to talk about and look at VDM in a lot more detail. We are going to look at VDM, actually another model-based specification language known as Z, which is kind of based upon VDM. It uses a lot of concepts from VDM, but it has its own special characteristics which makes it more powerful, and we will be looking at the model-based specifications in more detail in the case of Z specification. But since VDM was the first one in that sort of domain, and it gave the inspiration to others, so from an historic perspective, it is important to understand what VDM is. At least we should know what VDM is, because a lot of literature talks about VDM. So let me give you a brief history of VDM, and then we will talk about what this model-based specification is all about and how we can use VDM to build model-based specifications. So let me take you to the slide. VDM, as I mentioned earlier, is abbreviation of Vienna Development Method. The name Vienna came from the city of Vienna, and this whole paradigm or this whole set of languages, it originated through the work done at IBM's Vienna laboratory in 1970s. So initially, there was this Vienna Definition Language, or VDL, which was used to specify the semantics of programming languages, and it was first used to specify the semantics of programming language PL1. So that was Vienna Definition Language, or VDL. Later on, through evolution, Vienna Development Method, or VDM, was sort of invented, and it attempted to cover all software lifecycle, not just specification of the semantics of programming languages, but the entire software lifecycle. So basically, something that was supposed to be applicable for the entire development lifecycle. So that is why the name Vienna Development Method, VDM. VDM now has a specification language which is called VDM SL, and there is an extended form of VDM, that is VDM++, which supports the modeling of object-oriented and concurrent systems. This VDM like I mentioned earlier, it was originated from Vienna. IBM had a lab there, and the scientists there, they came up with this new mechanism to specify the semantics of programming languages, and hence the method was known as VDL, Vienna Definition Language. But then they thought that it should be used for the entire software development life cycle, and then it was at other laboratories of IBM, especially in England. People started to work at it, and they came up with this VDM. VDM, like I mentioned earlier, gave inspiration to many model-based specification methods and languages. The most famous of these are the B method and the Z specifications. We are going to look at Z in a lot of detail, and in the subsequent lectures we will discuss it in detail. So that will come later. Z has been in use for quite some time, and there have been a number of success stories associated with Z. Although VDM was also used and had some good success stories, but relatively speaking, it is difficult to use VDM as compared to Z, and that is why Z became more popular. Anyway, VDM has a number of extensions. The first one is the VDM specification language, or VDM SL, which is used to specify the behavior of the entities or the programs. And the second one is VDM++, just like we had C, and then from there we had C++. So they use the same kind of notation from VDM to a new VDM which supported object-oriented paradigm. So hence the name VDM++. And it also supported the specification of concurrent systems. Concurrent system specification we shall discuss later towards the end of this course. But most specification languages, they do not take care of the concurrent aspects of the system. They only talk about the sequential part. So the VDM originally only was meant for the sequential behavior, but this VDM++ also can specify the behavior of concurrent systems. And there are other extensions also. A number of tools are also available for VDM. Anyway, let us go back to the slide and look at it, this VDM, with the help of one example. So here is the example. What we want to have is, we want to specify the behavior of an incubator. In the incubator, the temperature needs to be carefully controlled and monitored in order to provide the correct conditions for a particular biological experiment to be undertaken. The temperature of the incubator increments or decrements in response to instructions, and each time a change of 1 degree has been achieved, the software is informed of the change, which it duly records. And finally, safety requirements dictate that the temperature of the incubator must never be allowed to rise above 10 degrees centigrade, and nor should it fall below minus 10 degree centigrade. So, ये बहुत simple सा एक incubator है which is used for biological experiments. The idea really is to have a controlled environment जिसमें आप temperature को एक within certain limits आपने control करना है और monitor करना है, ताकि आप अपना experiment वो controlled तरीके से आप कर सकें. So the very simple requirements are that there are a couple of operations, and those operations are increment temperature and decrement temperature, जो temperature को increment और decrement करने के लिए इस्तेमाल होगा. So when you give this command increment, it will add 1 to the temperature, and the temperature will be 1 more. Then so the heater will make sure that the temperature rises. and then if you decrement, then the temperature is supposed to come down by 1 degree. Similarly, there is this constraint that the temperature should never fall below 10 degrees centigrade and it should never be greater than 10 degrees centigrade. So हमारे पास एक कंडीशन है, कंस्ट्रेंट है, और हमारे पास बेसिकली बिल्कुल छोटा छोटा सा दो ऑपरेशंस हैं, इसके अलावा कुछ नहीं है. So let us look at, if we had to model it in a UML, what would it look like? This incubator, the object or the class for incubator would look like the one that I will just show you in UML. So here is that incubator class. So we have this incubator monitor. It has one variable temp for temperature, which is of type integer. We have two operations, increment and decrement, and the third get temp, which gives you the value of the temperature there. So what we have here is a very simple class in which there is only one variable, that is the temperature of the incubator. So that is the state that we want to maintain. So ये हमारी सिस्टम की स्टेट है, इस ऑब्जेक्ट की स्टेट है, ये इस क्लास की स्टेट है जिसको हमने मॉनिटर करना है. And then there are couple of operations which manipulate the state of this object, that is the increment and decrement, जो हमने इससे पहले देखे थे. और एक तीसरा method, that is we want to get the value of this temperature in the incubator, so we have the get temperature. So the important cheese to remember here is that although this is a class, in this class we have the state, and that state is maintained in the temperature variable, which is of type integer. इससे पहले algebraic specifications जो हमने देखी थी, उसमें state का concept नहीं था. On those algebraic specifications, we sort of, in some cases, we introduced some variables, but those variables did not have anything with the state of the object itself. They were there to help us specify the behavior of the system. Nothing more than that. But in this particular case, we are talking about the internal state, and then we shall say and see how these operations, that is the increment, decrement, how do they actually change or manipulate the state of the object. यहाँ पर एक चीज़ ज़रा आप जहन में रखिएगा कि जब हम इसको डिस्कस करेंगे, जब इसको देखेंगे, तो आपको ये बहुत इससे पहले जो हम डिस्कस कर चुके हैं OCL, ऑब्जेक्ट कंस्ट्रेंट लैंग्वेज, ये बहुत हद तक आपको उससे मिलती जुलती कोई चीज़ नज़र आएगी. जिस तरह के मैं पहले कह चुका हूं कि इन सारी स्पेसिफिकेशंस की रूट्स एक ही जगह से निकली हुई हैं, दैट इज़ दैट होर्स लॉजिक, और उसी के बेस पे मुख्तलिफ लोगों ने मुख्तलिफ टेक्निक्स डेवलप की हैं. तो यहाँ पर भी हम उसी तरीके से देखेंगे कि देयर विल बी प्री कंडीशंस, देयर विल पोस्ट कंडीशंस. जिस तरीके से ऑब्जेक्ट कंस्ट्रेंट लैंग्वेज में हमने देखा था कि देयर वाज इनवेरिएंट्स, यहाँ पर भी इनवेरिएंट्स होंगे, बट स्टेट का कॉन्सेप्ट यहाँ पर भी है, जो शायद इससे पहले ऑब्जेक्ट कंस्ट्रेंट लैंग्वेज में भी थोड़ा सा हमने देखा था, लेकिन एक्सप्लिसिटली हमने उसके बारे में बहुत ज़्यादा बात नहीं की थी. लेकिन यहाँ पर हम स्टेट के बारे में एक्सप्लिसिटली हम बात करेंगे. सो लेट मी take you back to the slide once again. So what we need to do is, the first thing that we need to know is how to specify state in VDM specification language, or VDM-SL. As mentioned earlier, state refers to the permanent data that must be stored by the system and which can be accessed by means of operations. The state is specified by declaring variables in a very similar manner to the way that is done in a programming language. So we have the variable name and type. So couple of things here. जिस तरीके से मैं पहले कह चुका हूँ, स्टेट उसी तरीके से है जिस तरह आपके एक ऑब्जेक्ट के इंटरनल डेटा स्ट्रक्चर्स हैं. So here once again we will define those kind of variables. that will maintain the state. And state क्या है? So state वो चीज़ है जो persistent data की हम बात कर रहे हैं. किसी ऑब्जेक्ट का persistent data, जो permanent data है, जो हम maintain कर रहे हैं data, जो आपके temporary variables हैं, they are not part of the state of the system. And in VDM SL, the state is defined in a way which is very, very similar to the way we define state in our programming languages. We will have the variable name and we will give its type just like we do in our programming languages. So let me take you back to the slide and continue this discussion. So in order to specify the state, we start with some built-in types which are available in VDM SL. We use mathematical notation. So the built-in types that we have, that is, we have the natural numbers, n, which are positive whole numbers. We have n1, which is natural numbers excluding 0. We have z, which are integers, positive and negative. We have r, the real numbers, positive and negative numbers that can include a fractional part. We have Boolean values, true or false, and we have characters, set of alphanumeric characters. So the intrinsic types that are supported in VDM SL are the basic numbers, that is the real numbers, the integers, positive, negatives, and then the whole numbers and the natural numbers. So जैसा कि हम सब जानते हैं कि these are the basic numbers, although there are other types of numbers, but we will be working with only these numbers. That is the real numbers, the integers, the whole numbers, and the natural numbers. And then we have the Boolean data type, and finally we have the character data type. So ये बिल्कुल basic सी हमारे पास data types हैं which we will use to build our specifications. We can have other things as well, but those complex data types will come a little later. So these are the basic intrinsic data types. How can we use these data types to build our specifications? Let us see, and let us work with the example of that incubator. So here is the state definition of the incubator. In the incubator monitor, we had this variable temperature. So that forms the state of the incubator monitor. So we say state incubator monitor of temp z. That is, it is an integer which can have positive or negative values, and it is enclosed within these, that is state, the name of the entity that we are defining. So we say state incubator monitor of, then we provide the state definition, and then we terminate it with this keyword end. So this state definition is a very, very simple kind of mechanism. Nothing very complicated. All we have to do is we start with this keyword state, give the name of the entity for which we are defining the state. So we say state of this thing is, and then we provide the variables and the type of the variables. So temp is of type integer. Remember that we said that it could have values between -10 and +10 centigrade. So this is of type integer, which can have negative and positive values. And then we say, okay, this is the end of the state definition by giving the keyword end. Very simple, nothing very difficult about it. Now let us look at the operations. So the first operation that we have is the increment operation. The increment operation is supposed to take the current value of temperature and increment it by 1, and it has to make sure that the value does not exceed 10, because that is the maximum upper limit. So this is what we are going to specify. So we say increment, that is the name of the operation for which we are giving the specification, extwr temp : z. So the first thing here, extwr temp colon z. This temp colon z is our state variable. Remember, we defined this temp of type z, of type integer. And we say ext stands for external, and wr means writable. So we are saying that we have rights, access rights to this variable temp, and we may modify the value. We can write or change the value of this particular variable, and we give this extern. This extern is kind of an external to this specification. That means, we could probably have some local variables. This is not a local variable. This is an external variable, and only a variable which is defined as external can be used in our specification in the post condition that we shall see. So we write this keyword extern. WR is the access right. We could have the read only, or we could have read write. In this particular case, we can say if we want to modify, we must have the right access to it. And then we give the name of the variable or name of the variables if we have more than one variables that come in the specification. The rest will be very, very similar to what we have seen earlier in the case of OCL and similar specifications. We would have the precondition and we would have the post condition here. The precondition in this particular case is what? We are saying that we want to increment the value of this temperature by 1, and at the same time there was this constraint that required that we could not have a temperature value greater than 10. That is, the maximum value is equal to 10. That also means that when we apply the increment operation, the value has to be less than 10. Only then can we increment the value by 1. If it is equal to 10, for example, we cannot increment because then it will become 11. That is not allowed. So this is what we will write in the precondition, and in the post condition we will write that the value is incremented by 1. So let us look at the pre and post conditions. Once again, nothing very special about it, as we have seen very similar specifications in the previous languages. For example, OCL, I have been mentioning this. The only difference is that we have a slightly different notation here. Nothing else, nothing very unusual about it, but only a new notation. So let us look at it. So the precondition, as mentioned earlier, temperature has to be less than 10. Only then can you increment its value. And the post condition is temp is equal to temp bar plus 1. Once again, this post condition, the concept is very, very similar to what we have seen earlier. We have the old value of temperature and we have the new value of temperature. The old value is denoted by the bar on it. Remember, we had similar specifications when we were writing the pre and post condition for our functions. So it is basically the same concept that we have, the old value and the new value. Another important thing to remember and note here is, then when we say temp is equal to temp bar plus 1, this is not an assignment. This is an equality. This is a Boolean expression, not an assignment. So we could have written temp bar plus 1 is equal to temp, the same thing. Or we could have written temp minus temp bar is equal to 1. Once again, the same thing. So this is an assignment. This is not an assignment. This is an equality. This is a Boolean expression. So this is what you must keep in mind. Now let me take you through to the rest of the specifications. The decrement is going to be very, very similar, nothing very new in the decrement part, but there will be slightly a new concept in the get temperature. So I'll very quickly show you the decrement and then I will move on to the get temperature. So in the case of decrement, we have this decrement external writable temp which of type Z. The precondition here is temp is greater than -10. So remember that we cannot have a value less than -10 after this operation is applied. So that is why we require that the temperature must be greater than -10 before this operation is invoked. And the post condition once again is again very similar. Temp is equal to temp bar -1. So nothing very special about it, but just wanted you to show this thing. Now let us look at the operation get temp. In this particular case, it returns an integer value back. So we say get temp returns a value current temp which is of type integer. So that is the name of the value that is being returned because we want to talk about it. What is this value equal to? So we are giving it a name. In this particular case, since this get temp only looks at the value and returns that value when this query is made, therefore it is not supposed to make any changes to the state of the object. Therefore we say external rd temp z. And in this particular case, this temp z, which the temperature which is of type integer, that is the variable, we give it the read access only, no write access. And the precondition in this particular case is true. There is no precondition applicable. And the post condition is that this current temp, that is the value that is being returned, is equal to the temp, that is the state of the object. यहाँ पर आपने देखा एक तो हमने नया कॉन्सेप्ट ये इंट्रोड्यूस करवाया कि ये जो एक्सटर्नल वेरिएबल टेम्प है, इन दिस पर्टिकुलर केस इट इज रीड ओनली, बट आई had mentioned that earlier also, so there is nothing really new about it. कोई इसमें खास बात नहीं है. The second important concept here is the name of the return value. In this particular case, the return value is assigned a name, kind of a variable that we have. Not just a type, like in our programming languages, when we write a function, we simply write down the type of the return value. We do not give it a name. We do not give the name to that return value. In this particular case, we are giving it a name because once we gave it a name, then it is easier to talk about that particular value, which value is being returned. So this is what we have here. So that is slightly different than what we do in our programming languages, but I hope the concept itself is not very, very difficult. So nothing really very special about it. Now let me take you back to the slide and move on to some new concepts there. In VDM, we can declare constants also. So constants are declared by giving the keyword values, and then we can give some names. So we have max, which is of type Z, and the value is 10, and min, which is of type Z, and the value is -10. So this is our limit. So once we have these constants declared, we can write our conditions using these constants. For example, here we can write the precondition that the temperature is greater than min, the precondition for the decrement operation. Then we have the concept of state invariant. The concept of state invariant, we have seen that earlier or also. जिस तरीके से मैं इससे पहले जिक्र कर चुका हूं, in our object constraint language, we have the concept of the state variable. And some of the other notations that we saw, they had the concept of state variable, state invariant also. The invariant, as we already know, means that whatever happens, we are saying that this condition cannot be violated. So that is the state invariant. VDM also has this notion of state invariant, and actually it is the first language that introduced the concept of state invariant. And then that concept was taken by others and was incorporated in those languages also. So how a state invariant is defined and declared in VDM, let us look at this notation. A state invariant, we say INV, which stands for invariant, MK dash incubator monitor T. And then we have this delta, which is underscored, and then we have min is less than equal to T is less than equal to max. INV stands for invariant. This expression MK incubator monitor is the input to the invariant function, and this expression is itself a function and is known as a make function. MK is pronounced as make. And this delta underscore is read as is defined as. So this invariant make incubator monitor T, where T is the variable there, is defined as min is less than equal to T is less than equal to max. That is, the value of T is greater than equal to min and is less than equal to max. So once again, we have seen the concept of invariant, and here the only difference really is the notation. Two new things in the notation that we have seen here. One is the INV itself, okay, and then we have the MK, MK and the name of the function, which is a function which is an input to the invariant expression. And this function MK stands for make. We say make this function T, and the condition that we specify is that this temperature is not going to be less than 10 degrees centigrade, and it is not going to be greater than 10 degrees centigrade. It is going to be something in between. So whatever you do, you increment, you decrement the value of this invariant. This invariant should not be violated. So the value of T must remain between minus 10 and plus 10. That is the minimum value and the maximum value. The condition itself is not very difficult, but the concept, once again, I wanted to show you the concept here. Then you would have noticed that we have some problem with the specification, and that is we do not know from where to start. What would be the initial value of this T? So we can specify an initialization function, which is init MK incubator monitor T is defined as T is equal to 5. So in VDM SL, we can also define the initialization function, which will set the values of the state variables to some initial value. It is just like a constructor function in our object-oriented paradigm. So you see कि किस तरीके से हमने इसकी इनिशियलाइजेशन के बारे में भी हमने बात कर दी. सो पॉइंट यहाँ पर ये है कि आपने शायद ये चीज़ नोट की होगी, देखी होगी, that this thing, this mechanism is very, very close to our programming languages, and hence it is, relatively speaking, more popular as compared to abstract algebraic specifications. But let us continue this discussion on model-based specifications and VDM, and see what else does it offer. In VDM, we have different types of collections that we can use, and these collections are sets, maps, and sequences. There are a number of operations that we can perform on a set. So these operations are enumerated here. The first is this brace A, B, C. So this is a set enumeration operation. It gives us the set of elements A, B, and C. We can use the set builder notation also. We have this X vertical bar, X colon T, and PX, which says this is the set of X from type T such that this PX, this condition, is met. Then we can have the ranges defined. We have I, dot, 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 comma, J, which is the set of integers in the range I to J. We can have also the member that is E in set S. We say that E is an element of set S. E not in set S, that is E is not an element of set S. Then we have the other set operations. We have S1 union S2, which gives us the union of sets S1 and S2. S1 inter S2 gives us the intersection of sets S1 and S2. S1 slash S2, which gives us the set difference of sets S1 and S2. Then we have the D union S, which is the distributed union of set of sets S. So this S is a set of sets. We are taking the union of all those sets which are member of this set S. Then we have S1P subset S2, which is S1 is a proper subset of S2. And we have S1 subset S2, which is S1 is a subset of S2, not necessarily a proper subset. And card S gives us the cardinality of set S. So, ये आपने देखा set में there is nothing very unusual about it. The only thing is that we can have a set of sets, और उसके ऊपर भी हमने union operation हमने define कर दिया D union. So we define a set of sets and we say D union of all those sets, and that gives us a convenient way of taking the union of more than one sets, more than two sets. So that is a convenient way of doing things. Then we have operations defined on the other types of collections, that is the maps and sequences. Let us very quickly look at those. So the main operations on sequences are bracket A, B, C using the square brackets. This is sequence enumeration, the sequence of elements A, B, and C. Then we use the kind of set builder notation, f of x, vertical bar, x colon t and p of x, which says sequence of expressions f of x for each x of numeric type t such that this p of x holds. So x values are taken in numeric order. Then we have head of S, HDS, which takes the head, that is the first element of S. Then we have tail of S, that is TLS. The tail remaining sequence after head is removed of S. Length of S gives us the length of S. Elements S, the set of elements in S. SI gives us the ith element of S. S1 and hat S2, the sequence found by concatenating sequences S1 and S2. So once again, nothing very special about it, but now we have a sequence which looks like a list in our Prolog programs. The notation is very, very similar to Prolog, but there are some differences here also, but nothing special here that we have. We have seen similar things earlier on as well. Now let us look at the last one, that is our map. The main operations on mappings are first is the mapping enumeration, which is brace A, vertical bar, then this arrow R, B, vertical bar. This arrow S means A maps to R and B maps to S. Then we have the similar comprehension notation, that is X bar arrow fx maps to fx vertical bar x colon t and px. That means x maps to fx for all x of type t such that this condition px is fulfilled. Then we have domain of M, dom M, which is domain of M, RNG M, which is the range of M, and MX, M applied to X. Then we have M1, M union M2, which is union of mappings M1 and M2, and M1 and M2 must be consistent where they overlap, and we have M1 plus plus M2, that is M1 is overwritten by M2. So in this particular case, we have this map. As we all know, this map is an attribute value pair. We say this value maps on to this value, and this map is a very useful collection, and that can be used to build our data structures or define our data structures. So that is why we have it here. The couple of things, except for the notation or the giving the elements of this, the one operation is of interest, the last two operations that I showed you, especially the last one, where we have M1 plus plus M2. That is, now this map M1 is replaced by this map M2. So sometimes you want to replace those values, so this is the operation given by the plus plus. So basically, like we have always been discussing, that formal specifications of formal languages, they rely very much upon the mathematical notations and the sets and those kind of things, and that is what we have seen in this particular case also. VDM, like I mentioned earlier, was the first of its kind which gave us the concept of model-based specifications. It is slightly difficult to write large specifications in VDM. VDM has many extensions which have made it possible to now build specifications, but the original form of VDM, in its original form, it was very difficult to write large specifications. But it gave this new concept, that is model-based specifications, in which the internal state is represented, and then we specify how that state is manipulated with the help of these operations and what are the changes to those states. Different researchers, they took the inspiration from VDM, and they came up with other models and other specification techniques. We have seen the previous cases, the object constraint language, which looked very, very similar to this model-based specifications. Lots of concepts, they were there. But the one language that was inspired really by VDM is known as Z. And that language now there are a number of interesting features that made it possible to write large specifications in form of pieces, small pieces. So from next lecture onward, we will be discussing Z, not VDM. VDM is a historical, very important landmark in our problem specifications. That is why we discussed here. But we will be discussing Z as a language for model-based specifications. Till that time, आप मुझे इजाज़त दीजिए. खुदा हाफिज़ और अस्सलाम वालेकुम.